Hello friends, welcome to UGC EPG Pathshala. I am Dr. Lubna Siddiqui, Assistant Professor, Department of Geography, Jamia Millia Islamia, New Delhi. Today I am going to discuss about the module Forecasting and Early Warning for Disasters, which comes under the paper Disaster Management. The rationale behind this module is India is a land of varied hydrometeorological and geophysical characteristics with two monsoon seasons, northeast and southeast, two cyclone seasons, that is pre and post monsoons, summer characterized by significant rise in mercury levels and winters characterized by significant drop in mercury levels. 87% of disasters are related to climate-related extreme events and affects roughly 1.7 billion people and economic cost of $1.4 trillion according to UNISDR 2015. The number of people impacted due to extreme events could be reduced by adopting appropriate forecasting and early warning system. The learning objectives of this module are: number 1, to understand forecast and early warning; number 2, to understand essential elements of early warning system; number 3, to acquaint with historical trajectory of early warning system; number 4, to understand early warning systems in place in India for different hazards; number 5, to understand key issues in the design of effective EWS; number 6, to acquaint with the benefits of EWS. This module is divided into 3 sections. Unit 1, Forecasting and Early Warning. Now forecasting. Meteorological science or meteorology concerned with the study of atmosphere as a means to forecast the weather is an important component of disaster management. Forecast implies an indication of the likely occurrence or non-occurrence of a future event. Forecast may or may not imply a negative outcome, for example, weather forecast. This includes the following: number 1, information pertaining to severe weather event; number 2, the location, size and intensity of the weather event; number 3, the path trajectory of the propagation of weather event, that is, in the case of tornado, the path followed on the basis of the thunderstorm characteristics and wind condition. Number 4, determining accuracy of previous estimates. Any forecast of a probable extreme weather event is followed by early warning, wherein the dissemination of forecast takes place with the consideration of factors like questions of who receives the information about the forecast, how quickly, and along with the recommendation of the best course of action to mitigate the impacts of the impending extreme weather event. Now, early warning system. A warning connotes a negative outcome, for example, a cyclone warning or a flood warning of the occurrence of the prospective disasters. Early warning system is the hard and soft system in place that helps in generating and disseminating meaningful and important timely information about a warning that would enable individuals, communities and organizations to prepare and appropriately act to the impending hazard in order to reduce the likely losses or harm according to UNISDR 2009. Early warning systems are highly complex due to variation in space, that is global, national, regional or local, hazard onset, that is rapid or slow, hazard frequency, goals, that is provide safety, protect property or environment, hazard types, that is hydrometeorological, geological, climatic or health, and the economic, political and societal context where they operate according to Carolina Garcia 2012. Early warning system brings together multiple institutions and organizations to to communicate to all relevant stakeholders such as scientific community, civil authorities, media and public. The EWS acts as the medium through which an unusual weather pattern is recognized as an aberrant from predictable weather pattern and is communicated to people at risk to ensure response from the people, and the administration reduces the impacts of the unusual weather. An effective early warning system thus consists of 4 elements as shown in figure 1. Number 1, risk knowledge, which includes A, knowledge about the usual weather pattern, B, investigation and analysis of the localized unusual weather pattern, number C, the likelihood of people or area at risk of impact due to the unusual weather pattern, number 2, monitoring and warning service, which include number A, monitoring of regular climate and other hydrometeorological factors in order to know what and when extreme weather events could occur. B, effective and timely warning raised during the extreme weather conditions. Number 3, dissemination and communication, which include A, communicating about the warning and its potential impact, B, to disseminate meaningful and action-oriented information to the right audience that includes the people at risk and the decision makers that respond to the event by mobilizing resources in order to reduce impact at the right place. Number 4, response capability, which include A, ensuring the required response systems are activated in order to reduce the impact. Number 1, response system for policy level responders, that is administration, NGOs, etc. Number 2, response system for the community, that is their level of awareness and their response to the early warning, trusting the message bearers and initiating the necessary response depending on the type of event. B, if found unsatisfactory, appropriate action to raise the response capability for reducing the impact of future events. Figure 1 shows the elements of early warning system. An early warning enables by way of its warnings, that is outlook, watches, warning and alerts to at-risk population to take, that is or not to take appropriate preventive actions. It guides various agencies and governmental organizations to develop strategies to respond to current as well as future impacts of hazard in better manner. Now, historical evolution. Early warning system, that is EWS, gained attention in the 1970s and 1980s during the extended drought and famines in the West African, Sahel and Horn of Africa, according to Glantz 2004. Famine early warning systems, that is FEWS, were developed in at-risk countries and regions in the sub-Saharan Africa with the help of international organizations. The famine early warning system, that is FEWS, in response to the famines in Sudan and Ethiopia, was amongst the first modern utilization of early warning system. This was followed by the recognition of the necessity of early warning system by the United Nations during the International Decade for Disaster Risk Reduction. The Yokohama Strategy in 1994 further acknowledged early warning as a crucial component of disaster management. UN International Strategy for Disaster Reduction called for the academic research on early warning from technical and social perspectives. The 2004 Indian Ocean tsunami that claimed over 2 lakh lives was a major turning point in realizing the urgency to develop early warning system. An Intergovernmental Oceanographic Commission was set up for developing a global early warning system framework for ocean-related hazards. In 2005, the Hyogo framework increased the focus on preparedness and early warning by including risk assessment and EWS as one of its 5 themes. In 2006, UNISDR developed a checklist for early warning system to aid governments in reducing impacts across the world. The Tohoku earthquake in 2011 put to test the increased preparedness through effective EWS in Japan that included the early warning, evacuation routes, and coordination amongst various stakeholders. Figure 2 depicts the historical evolution of recognizing EWS in disaster management. Figure 2 shows the milestones in development of early warning system. Presently, early warning systems are in place for multiple hazards such as technological, hydrological, meteorological as well as anthropogenic. Now, objectives of early warning system. Number 1, life savings. Several countries have reduced the number of casualties in extreme events by developing and implementing effective and efficient early warning system and disaster response. Number 2, damage prevention. With prompt and timely warning, the damage to infrastructures can be reduced at the significant level. In slow onset disasters, early warning system can provide enough time to put adequate measures such as retrofitting the buildings and construction of barriers. Now, the second section deals with early warning system across hazards. India being a multi-hazard prone country, there are multiple threats of disasters throughout the year. The table below mentioned presents the agencies designated for early warnings related to different kinds of hazards. Table 1 shows agencies for early warning disseminations in India. Cyclone early warning system in India. In India, the early warning system for tropical cyclone is entrusted to Indian Meteorological Department, that is IMD, which classified the cyclone according to wind speed. This classification is given in Table 2. Table 2 shows the IMD classification of tropical cyclone. During the years between 1981 to 2002, states on the eastern coast, that is West Bengal, Odisha, Andhra Pradesh, Tamil Nadu, have faced 6,99,879 and 54 cyclones respectively according to NDMA 2008. Odisha, for example, faced 98 cyclones in districts of Balasore, that is 32, Cuttack, that is 32, Puri, that is 19, and Ganjam, that is 15. On the other hand, western coastal states have faced cyclones much lesser in frequencies as compared to the eastern coast. These are Maharashtra, that is 13, Gujarat, that is 28, Kerala, that is 3, Karnataka and Goa, each 2. There is a systematic approach of cyclone warning in India as developed by IMD. The cyclone warning system is divided into 4 stages. Number 1, pre-cyclone watch, issued when a depression forms over ocean and likely to affect the Indian coast in future. This bulletin issued at least 72 hours in advance. Number 2, cyclone alert, which is also referred as yellow message. This warning is given in initial days or development phase of the cyclone prior to 48 hours before. Number 3, cyclone warning, which is also referred as orange message, issued at least 24 hours when the cyclone is located within 500 km from the coast. Number 4, post landfall outlook, issued at least 12 hours before the cyclone landfall when cyclone is located within 200 km from the coast, referred as red message, provides information on the likely area of landfall and the weather expectation in interior areas that helps administration to prepare for evacuation or other measures to reduce impacts. This nomenclature is used in all the warnings issued by IMD. Odisha, that is Orissa, and Andhra Pradesh, the most cyclone vulnerable states in India that witness the maximum number of cyclones, are also amongst the most prepared states. Sharp reduction in the casualties post-Falene compared to the destruction during the supercyclone of 1999 stresses the effectiveness of the early warning system. During Falene, the Indian Meteorological Department accurately predicted the wind velocity, which contributed to better forecast and effective warning communication. This early warning enabled coastal villages to be evacuated in Puri and Ganjam district of Odisha. Ganjam and Puri districts received special warnings from the Odisha State Disaster Management Authority on 10th October, 2 days before the landfall of cyclone. This prompted the evacuation of as many as 1,02,000 residents in Puri and 1,80,000 in Ganjam district. Early warning communicated through email, telephone and print media, online news networks, PA systems as well as satellite phones. Now, Indian Tsunami Early Warning System, that is ITEWS. The Indian Ocean Tsunami, that is 2004, demonstrated the extreme vulnerability of the Indian coast to tsunami. The massive earthquake on December 26 in the Indian Ocean triggered a large tsunami waves, resulting in colossal loss of lives and affecting millions of people in 11 countries, according to Dash 2005. After the occurrence of tsunami, Indian Tsunami Early Warning System was established in the Indian National Center for Ocean Information Services, that is INCOIS, Hyderabad, under the Earth System Science Organization, that is ESSO of Government of India. ITEWS became operational in October 2007. Now, components of the ITEWS. The Government of India had decided to adopt early warning system in India, and therefore a tsunami early warning system was installed. The Indian Tsunami Early Warning System consists of a real-time network of seismic stations across India, bottom pressure recorder, that is BPR, tide gauges and a 24/7 dedicated warning center. The mandate of ITEWS is to detect tsunami-genic earthquakes, to monitor tsunamis and to provide timely advisories with the help of previous scenario database, vulnerability modeling and decision support system, according to Kumar and Nayak 2010. Table 3 shows the tsunami bulletins. Now, early warning system for flood. Indian subcontinent is prone to floods in our well-endowed river systems. Figure 4 shows the flood-prone areas in India, the source of which is NDMA guidelines. Figure 4 shows the areas liable to floods in India. Flood forecasting and warning activities in India are taken care of by the Central Water Commission, that is CWC, which covers most of the flood-prone interstate river basins in the country. CWC presently issues flood forecast for 175 stations, out of which 147 stations are for river stage forecast and 28 for inflow forecast, that is National Disaster Management Guidelines Management of Floods 2008. Very high frequency or high frequency wireless communication systems are used for data collection at forecasting centers. The final flood forecast are communicated to the concerned administrative and authorities such as state or central governments, district magistrate through special messenger or telegram or wireless or telephone, fax, email, etc. Flood forecast information is disseminated through All India Radio, that is AIR, Doordarshan and print media for wider publicity across the country. In Assam, the flood early warning system, that is FLEWS project is being executed on the operational basis. It is terrain specific and utilizes satellite based inputs, in situ data on rainfall and river discharge at key crucial points. Now, early warning system for heat waves. Indian Meteorological Department, that is IMD, declares heat wave when a. Normal maximum temperatures of a station is less than or equal to 40 degrees Celsius. Number 1, heat wave departure from normal is to 5 degrees Celsius to 6 degrees Celsius. Number 2, severe heat wave departure from normal is 7 degrees Celsius or more. B, normal maximum temperature of a station is more than 40 degrees Celsius. Number 1, heat wave departure from normal is 4 degrees Celsius to 5 degrees Celsius. Number 2, severe heat wave departure from normal is 6 degrees Celsius or more. C, actual maximum temperature remains 45 degrees Celsius or more irrespective of normal maximum temperature, heat wave situation may be declared. The extreme temperature of heat waves killed about 3,000 people in 1998 and more than 2,000 in 2002. Heat wave caused over 2,000 deaths in 1998 in Odisha and more than 1,200 deaths in 2002 in southern India. According to Prevention and Management of Heat Wave 2016. The casualties due to heat waves show that heat wave is a significant hazard and thereby necessitates the development of early warning system. Heat wave need not to be considered till maximum temperature of a station reaches at least 40 degrees Celsius for plains and at least 30 degrees Celsius for hilly regions. IMD performs meteorological observation and provides forecast of weather sensitive activities. IMD provides real-time data and weather prediction of maximum temperature, heat wave warning, alert for the vulnerable cities, rural area of the severity and frequency. To communicate early warning to general populace, the Ahmedabad City Heat Action Plan came up with following color coding scheme. Figure 5 shows the color signals for heat alert. Ahmedabad in Gujarat is amongst the first states in India to have planned a heat wave action plan. Other cities and states are in the process of formulating heat action plan due to the significant number of affected individuals due to heat wave phenomenon, according to Ahmedabad Heat Action Plan 2016. Now, early warning system for drought. Drought is a slow onset event and affects the ecosystem by a prolonged period of reduced rains or other conditions that lead to reduced moisture content in the soil. Failed rainfall is a key component of drought conditions. Meteorological drought monitoring essentially consists of rainfall monitoring. IMD monitors daily and weekly real-time rainfall data and provides weekly briefings to Ministry of Agriculture in crop weather monitoring groups. Rainfall is monitored by district-wise rainfall monitoring scheme. The National Remote Sensing Center of ISRO, that is Indian Space Research Organization, supports IMD in monitoring drought situation through their NADAMS, that is National Agricultural Drought Assessment and Monitoring System. Drought assessment are done at district or regional level, and bi-weekly bulletins are issued during the monsoon season, that is from June to October. By utilizing spatial representation of data including different indices for drought assessment, NADAMS provides user-friendly information to the concerned state officials to respond to and reduce impacts of drought. Now, the third section of this module is prospects of early warning system. Risk communication. Early warning system is evolving due to increased awareness and necessity at the international and national level. The evolution of EWS has enabled critical life-saving response and preparedness actions. Inclusion of risk perception of the potentially affected community is much required for effective communication of risk conditions. People at risk are having perception of the imminent risk, and the success of any early warning system is in preparing a dissemination and communication system that takes into consideration the social dimension of risk perception and diversity of the perceptions from the community. Social amplifications of risk is possible due to the heightened personal interpretation of hazards risk, which need to be taken into consideration in devising the early warning system. Warnings against venturing out in the daytime in summer conditions during heat wave events, for instance, might not be interpreted as serious by farmers who need to venture out to their farms to prepare their fields for the oncoming monsoon season. Heat and the perception of heat is relative. Fishermen might not prefer vacating the coast even during cyclones in order to oversee and prevent damage to their fishing equipments. Now, rise of social media and other mass media for communication. With increasing usage of social media and mobile connectivity, early warning systems must be developed to suit the changing culture of communication. Fax and pager systems are obsolete. Nations worldwide are developing newer technologies to reach the maximum number of people at the shortest time to enable a quick and effective response. Early warning system must therefore be continuously updated with changing times. Now, concerns. Number 1, extreme climatological events wreak havoc majorly in the developing nations. These countries have limited capacity due to the infrastructure barriers and funding unavailability. Development in science, technology, and system governance could help in the reduction of impacts by reaching the right individuals at the right time. Early warning systems must be viewed as an investment and not an expenditure, as effective early warning systems lead to a great reduction in impact of extreme events. B. Changing nature of extreme events. The case study is Tsunami 2004. A great earthquake struck the Indian Ocean on 26 December 2004, leading to giant tsunami waves that caused significant damages to lives and property. India was also severely affected. The southern state of Tamil Nadu suffered major impacts. Prior to the year 2004, high-risk hazards in India did not include the tsunami. It was believed that tsunami occurs only in the Pacific Ocean. There was considerable research on the tsunami and reduction of its risk in various countries including Japan, but tsunami risk reduction measures were not considered as essential due to the extremely less probability. Now, benefits of a strong early warning system. A systematic and strong early warning system must consider these aspects as part of the key elements as shown in figure 1, that is systematic data collection and risk assessment, development of hazard monitoring and early warning services, dissemination and communication of risk information and early warning to all those at risk and to those who have the capacity to address the risk, and to finally build national and community response capacity. Insurance is seen as a major tool in disaster risk management, that is risk transfer. Sound EWS would have tremendous impact on the insurance and reinsurance industry. EWS would not only reduce the liability of insurance by reducing the adverse impacts, but would also lead to better modeling of insurance and reinsurance, thereby significantly affecting the industry. Increased capacity to address risk and reduced burden on insurance industries would significantly increase the resilience of the community to natural disasters. Now, summary. Number 1, forecasting and early warning systems are critical to deal with hazards. Number 2, forecasting is the likely occurrence or non-occurrence of future event. Number 3, warning connotes negative outcome and essentially requires responsive action. Number 4, the elements of early warning are: number 1, risk knowledge; number 2, monitoring and warning; number 3, dissemination and communication; number 4, response capacity. 5, objective of early warning, which includes: number 1, save lives; number 2, to prevent damage. Number 6, there are nodal agencies for early warning for different hazards. Number 7, risk perception of the community is an important component of early warning system. Number 8, EWS must consider the changing nature of hazards. Number 9, EWS must be updated with the advent in technology and social media. Number 10, accuracy of warnings play an important role in the response of the community to future warnings. Number 11, sound EWS would help build response capacity to natural disasters, significantly reduce liabilities for insurance and reinsurance sector, and help develop a resilient nation. I hope you have understood the concept of forecasting and early warning for disasters. See you next time. Thank you.